Hey there, science enthusiasts. Ever wonder what makes your lights turn on or how your phone magically talks to satellites far away? The answer, my friends, is electromagnetism. It's one of the fundamental forces of nature. You can't always see it, you can't always feel it directly, but it's everywhere. It's like a secret power woven into the very fabric of our universe. It's responsible for so much of what we experience. It's truly amazing stuff, you know. Now, why should you care about electromagnetism? Well, because it's incredibly cool and super important. This force is the superstar behind electricity. It's the magic in magnets. It's even light itself. Think about it. Without electromagnetism, our modern world just wouldn't exist. No light bulbs, no computers, no smartphones, no internet. It's the invisible engine driving so much of our technology and our understanding of the cosmos. It's a very, very big deal in science. Imagine, just for a second, a world without this force. It would be a pretty dim place, wouldn't it? No cozy lamps to read by, no beeping microwaves to heat your popcorn, no rock and roll on the radio. Our lives would be drastically different and probably a lot more boring. Electromagnetism is the unsung hero that makes our daily lives convenient, connected, and full of wonder. It's a fundamental part of what makes our planet, and indeed the universe, tick. So, are you ready to put on your thinking caps? Are you prepared to explore this fascinating force? We're about to embark on an electrifying journey. We'll uncover the secrets of electric fields. We'll delve into the mysteries of magnetic fields. We'll see how they dance together in a cosmic ballet. And we'll discover why electromagnetism is one of science's greatest hits. Fasten your seatbelts, everyone. Let's get started. Science rules. All right, let's zoom in on the E in EM. That stands for electric fields. And it all begins with something called electric charge. Tiny little particles in atoms have this property. You've heard of protons, right? They have a positive charge. Think of it like a little plus sign. Then there are electrons. They have a negative charge, like a little minus sign. These charges are the building blocks of all things electric. Isn't that just incredibly neat? It's fundamental. Now here's where it gets really interesting. These charges interact with each other in specific ways. Opposites attract. A positive charge and a negative charge will pull towards each other. They just can't resist. But what about charges that are the same? Well, like charges repel. A positive charge will push away another positive charge, and a negative charge will push away another negative charge. It's a basic rule of the universe, like a cosmic dance of push and pull. So what exactly is an electric field then? Imagine a charged particle. It creates an invisible area of influence all around itself. This area is where its pushing or pulling electric force can be felt by other charges. That's the electric field. You can't see it with your naked eyes, but trust me, it's there. It's like the particle's personal force bubble, a region where it makes its presence known. It's a powerful concept in physics, believe me. The strength of this electric field depends on a couple of things. A stronger charge creates a stronger field. Makes sense, right? More charge, more oomph. Also, the closer you are to the charge, the stronger the field will be. As you move further away, the field gets weaker and weaker. It's this very field that makes a balloon stick to your hair after you rub it. That's static electricity in action, powered by electric fields. Science is all around us. Next up, let's talk about the M in EM. That's for magnetic fields. These are just as cool as electric fields, if not cooler. You've probably played with magnets before, right? Those fascinating objects that stick to your refrigerator door, or the ones that can pick up paper clips. Most magnets you see have two special ends. We call them the North Pole and the South Pole. And here's a fun fact. You can't have one without the other. They always come in pairs. Just like with electric charges, these magnetic poles interact in predictable ways. Opposite poles attract each other. So the north pole of one magnet will pull towards the south pole of another magnet, and vice versa. They're drawn together like best friends. But what happens if you try to push two similar poles together? They repel. A north pole will push away another north pole, and a south pole will push away another south pole. Go ahead, try it with two bar magnets. It's a hands-on experiment. So what is a magnetic field? It's the region around a magnet where its magnetic force can be detected. This force is what makes other magnetic materials or other magnets move. The magnetic field lines are often shown as loops. They flow out from the North Pole and loop around to enter the South Pole. You can actually see the shape of these invisible lines. Just sprinkle some iron filings on a piece of paper above a magnet. The filings will line up and reveal the pattern. How cool is that? And get this, our very own planet Earth is like a giant magnet. It has a molten iron core that generates a massive magnetic field. This field stretches far out into space. It even helps protect us from harmful solar radiation. And it's the reason why compasses work. A compass needle is just a tiny magnet. It aligns itself with Earth's magnetic field lines, with one end pointing toward the Earth's magnetic north. Pretty handy for navigation, for explorers, and for science. So we've met electric fields and we've met magnetic fields. They both seem pretty important on their own, right? But here's the really mind-blowing part. They aren't totally separate things. Nope, they are deeply connected. They are like two superstars in a dynamic duo act. They are in fact two different aspects of a single, even more fundamental force, the electromagnetic force. It's a partnership that shapes our universe. This is where things get really exciting, folks. Here's one of the most amazing discoveries ever. A changing magnetic field can actually create an electric field. Think about that. Move a magnet or change the strength of its field and poof, an electric field appears. This incredible phenomenon is called electromagnetic induction. The brilliant scientist Michael Faraday discovered this in the 1830s. It was a total game changer. This very principle is how we generate most of the electricity we use every day. Generators use moving magnets to make electricity flow, and guess what? The universe loves symmetry. So, it works the other way around too. A changing electric field can create a magnetic field. Isn't that elegant? Or even simpler, if you have electric charges that are moving, that's what we call an electric current. They will produce a magnetic field around them. This was first observed by Hans Christian Ørsted. It showed a direct link. Electricity could make magnetism. This connection was a revolutionary idea at the time. This constant interplay, this back and forth creation, is the heart of electromagnetism. A changing electric field makes a magnetic field. That changing magnetic field then makes an electric field. And so on, and so on. It's like they're locked in an eternal dance. This dance creates waves, waves that can travel through empty space. These are called electromagnetic waves, and guess what? Light is one of them. So are radio waves, microwaves, and X-rays. Wow, this connection is just astounding. Section 5, Sparks of Discovery, Early Encounters with Electricity and Magnetism. People have been curious about electric and magnetic effects for thousands of years. Way back in ancient Greece, folks noticed something strange about amber. Amber is fossilized tree resin. When they rubbed a piece of amber with fur or cloth, it would suddenly attract lightweight things, like tiny feathers or bits of straw. The Greek word for amber was electron, and that, my friends, is where our word electricity comes from. Pretty neat origin story, huh? The ancient world also knew about another mysterious material, lodestones. Lodestones are naturally occurring magnetic rocks. They are a type of iron ore called magnetite. People discovered that these special stones could attract pieces of iron, and even more amazingly, if you floated a lodestone on a piece of wood in water, it would always turn to point in the same direction. This led to the invention of the very first compasses. Sailors used these to navigate the vast open oceans. Imagine that. For a very, very long time, these two phenomena, the static cling of rubbed amber and the pull of lodestones, seemed completely unrelated. They were just two separate curiosities of nature. One was thought of as electric stuff. The other was magnetic stuff. Nobody really suspected that these two seemingly different forces were actually deeply connected. The idea that they were two sides of the same coin was still centuries away. Science often starts with separate observations, but curious minds kept experimenting. Scientists in the 17th and 18th centuries started to study electricity more systematically. They built machines to generate static electricity. They invented the Leyden jar, an early type of capacitor to store electric charge. Then there was Benjamin Franklin. He famously flew a kite in a thunderstorm. A very dangerous experiment. Don't try it at home. But it helped prove that lightning was a giant spark of electricity. Slowly but surely, the puzzle pieces were being gathered. Section 6. Connecting the dots, key scientists and their aha moments. The real breakthroughs in understanding the connection between electricity and magnetism came in the 19th century. This was a golden age for physics. Scientists were buzzing with new ideas and experiments. One of the first big aha moments came from a Danish physicist named Hans Christian Ørsted. In 1820, he was giving a lecture. He had a wire carrying an electric current near a compass, and something amazing happened, purely by chance, some say. Ørsted noticed that when he switched the electric current on, the compass needle suddenly twitched. It moved from its usual north-pointing position. When he switched the current off, the needle went back. Whoa! This was a monumental discovery. An electric current moving electric charges could create a magnetic effect. It was the first solid proof that electricity and magnetism were not separate forces after all. They were related. The scientific world was electrified by this news. News of Ørsted's discovery spread like wildfire. In France, a brilliant physicist named André-Marie Ampère heard about it. He was fascinated. Within just a few weeks, Ampère conducted a series of ingenious experiments. He showed that two parallel wires carrying electric currents would attract or repel each other, just like magnets. He then developed mathematical laws to describe these magnetic forces between currents. Ampère laid much of the groundwork for the field we now call electrodynamics. What a mind! Then, across the English Channel, there was Michael Faraday. Faraday was an incredible experimental scientist. He had very little formal education, but he had an insatiable curiosity and amazing intuition. Inspired by Ørsted and Ampère, Faraday wondered if electricity can create magnetism. Can magnetism create electricity? After years of trying, in 1831, he found the answer. Yes, he showed that a changing magnetic field passing through a coil of wire could induce an electric current in the wire. This is electromagnetic induction, the principle behind electric generators. Faraday's work was truly revolutionary. Section 7, Maxwell's masterpiece, the Grand Unification. So we had Ørsted showing electricity makes magnetism. We had Faraday showing magnetism makes electricity. Ampère was writing down the laws for forces. The pieces of the puzzle were definitely on the table. But it took one more giant leap of genius to put them all together into one beautiful, complete picture. That genius was James Clerk Maxwell, a Scottish physicist with an incredible mind for mathematics and physics. He was born to unify. In the 1860s, Maxwell took all the known experimental results and laws from Ørsted, Ampère, Faraday and others. He synthesized them, he refined them, and he expressed them in a set of just 4 elegant mathematical equations. These are famously known as Maxwell's equations. Think about that. 4 equations to describe almost everything about electricity and magnetism. They are one of the greatest achievements in the history of science. They are like the poetry of the physical world. What Maxwell's equations showed with stunning clarity was that electric and magnetic fields are not just related, they are fundamentally intertwined. They are 2 manifestations of a single underlying entity, the electromagnetic field. One can't exist without influencing the other, especially when things are changing. This was a grand unification. It brought together seemingly disparate phenomena into one coherent framework. It was like discovering the secret language of these forces, a true triumph of human intellect. But Maxwell didn't stop there. His equations made an astonishing prediction. They predicted the existence of waves made of oscillating electric and magnetic fields. These waves would travel through space, and his equations even predicted the speed of these waves. When Maxwell calculated this speed, it turned out to be incredibly close to the measured speed of light. This led him to a profound conclusion. Light itself is an electromagnetic wave. This was mind-blowing. It changed our understanding of light and the universe forever. Section 8, Electromagnetism in action powering your everyday life. Okay, science team, all this history and theory is fascinating, right? But you might be thinking, Bill, how does this electromagnetism stuff actually affect my life? Well, let me tell you, it affects pretty much everything you do every single day. Just look around you. The lights illuminating your room powered by electricity, which is all about electromagnetism. The computer or phone you're using to read this, packed with circuits and components that run on electromagnetic principles. It's incredible. Think about all the gadgets and appliances that make our lives easier. Electric motors are a perfect example. They use the interaction between electric currents and magnetic fields to create motion, to make things spin. Your electric fan on a hot day, that's an electric motor. Your blender making a smoothie, motor. Your washing machine cleaning your clothes, you guessed it, an electric motor, and electric generators, they do the opposite. They use motion, like a spinning turbine, within a magnetic field to generate electricity, powering our homes, schools, and cities. And what about communication? Radio waves, television signals, Wi-Fi, Bluetooth, your cell phone calls. All of these are types of electromagnetic waves. They travel through the air and even through space, carrying information at the speed of light. Microwaves, another type of electromagnetic wave, cook your food quickly and efficiently in a microwave oven. Even X-rays, which doctors use to see inside your body and check your bones, are high-energy electromagnetic waves. It's a whole spectrum of power and utility. Even the very act of seeing the world around you is thanks to electromagnetism. Remember, light is an electromagnetic wave. These waves travel from the sun or from a lamp, bounce off objects, and then enter your eyes. Your eyes detect these waves, and your brain processes the signals into the images you see. The vibrant colors, the shapes, the motion, it's all interpreted from light. So from the grand scale of stars to the screen you're looking at right now, electromagnetism is truly everywhere, making things happen. Consider the following. Section 9, the future is electric and magnetic. What's next for EM? So there you have it. We've journeyed from ancient observations of static cling to the magnificent unification of electricity and magnetism by James Clerk Maxwell. We've seen how this fundamental force powers our world. Electromagnetism is undeniably one of the pillars of modern science and technology. It has revolutionized how we live, work, and communicate. But guess what? The story of electromagnetism is far from over. Scientists are always exploring, always pushing the boundaries. Not by a long shot. Scientists today are delving even deeper into the quantum world of electromagnetism. There's a theory called quantum electrodynamics, or QED for short. It's the quantum field theory of the electromagnetic force. It describes how light and matter interact at the most fundamental subatomic level. Think tiny particles like electrons and photons, particles of light doing their quantum dance. Physicists like Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga developed this theory, and it's one of the most precise and successful theories in all of science. Super advanced and super cool. And of course, we're constantly finding new and exciting ways to harness the power of electromagnetism. Engineers and inventors are working on things like even better medical imaging techniques. Think sharper MRIs. They're designing faster and more powerful computers and communication systems. Imagine more efficient ways to transmit energy wirelessly across vast distances, or super efficient wireless charging for all our devices. No more tangled cords. There's even research into using incredibly strong magnetic fields to achieve controlled nuclear fusion, a potential source of clean, limitless energy. The possibilities are truly electrifying. Electromagnetism is a fundamental force of nature that has profoundly shaped our understanding of the universe and transformed our civilization. From the simplest compass to the most complex supercomputers, its principles are at play. And as we continue to explore its depths and innovate with its applications, it will undoubtedly continue to shape our future in ways we can only begin to imagine. So, keep that curiosity alive. Keep asking questions. Keep exploring the wonders of science because, as we always say, science rules.